Okay, so you get these image reflections because of these waves being out of phase. They interfere in such a way that they get these interferences. And what I was talking about was we can use this knowledge, since we know the frequency, we know the wavelength of certain colors. When we see certain interference patterns, we can measure very small distances, like how thick a bubble is. Do you ever wonder how people know how thick a soap bubble is? They use this knowledge.
That's my dream.
I know.
How thick is a soap bubble?
Very, very thin. Okay.
Soap bottles, I'm pretty sure, are different.
So, this leads to a property called iridescence.
I don't like that.
Iridescence is when you get these rainbows from these thin films.
That's rainbow of colors, right?
That's an iridescence, yeah, it's a rainbow of colors. Created by thin film reflections of white light. And it's because the white light is reflecting from both surfaces. So for a soap bubble, the light is reflecting from both the top surface and the inside surface. And that difference in thickness of that soap bubble makes the light waves out of phase when they reflect. And when they're out of phase, they start interfering, canceling and creating different colors. So different colors refract and reflect from the layers, different media, interfere on the way back to what we're seeing. When the green is canceled, we get the magenta. When the blue is canceled, we get the yellow.
So we need to know that.
Good. It's a good idea to understand iridescence. But it's all caused because of this thin film reflections, where they're reflecting off both the top and the bottom part of the film. So this happens in soap bubbles. It's because soap's reflecting off the top and the bottom. Happens in the snake's scales, because the scales are basically see-through. So it's part of the white light is reflecting from the top, and part of the white light is reflecting from the bottom, the inside layer. And they start interfering. Gasoline, when you have gasoline on, or oil on the ground, it looks all rainbowy. It's because the light is going through the gasoline. Some light's bouncing off the top, and some light's going through and bouncing off the next layer down, either the water underneath it or the ground underneath it, and that creates this rainbow sheen because the white light is getting out of phase and reflecting. Call that iridescence.
Then how come if you pour vegetable oil on a road, will it become a rainbow too?
It depends. So every material has different properties of this. So most oils will do some form of iridescence. The interesting thing is the colors you see is based on how thick it is. So you can tell microscopic differences in thickness of this soap bubble by what colors you're seeing. If it's yellow, it's slightly, I don't know if it's thinner or thicker, but it's one or the other than the magenta part, than the blue part. Same thing with the oil or gas on the pavement. Slightly thinner and slightly thicker gives you different colors. So, lasers. Let's get to lasers. Laser stands for light amplified by stimulated emission of radiation.
I thought laser was spelled with Z.
Nope. Laser, L-A-S-E-R, light amplified by stimulated emission of radiation. It's an acronym. So that's what laser stands for. I know it doesn't make a lot of sense, but how it works is they bounce one electron to another, and those create a very specific beam. Anyways, this is normal light. We call it incoherent. Normally light is incoherent. It has all or many frequencies, and they're all in different phases. Some are out of phase, some are in phase, some are red, some are blue, some are green. All different light at different phases we call incoherent. That's what normally light is. When we have a monochromatic light, so like a red light or a green light, the light is all the same frequency, but it's still out of phase. Slightly out of phase. So some is further along than others. We call, that's how monochromatic, it's neither incoherent or coherent. Laser light is coherent, meaning that it is not only a single frequency, but they're all in phase. You see that in this bottom picture. So laser light is fantastic for labs because coherent light allows us to do much more specific and useful lab experiments. So we don't have to worry about the differences in phase throwing off our experiments. So anyways, laser light is very commonly used to prove a lot of these things that I've been teaching the last few weeks. But it's created once again by, they agitate a single electron. Remember, electrons vibrating is what causes a light ray. And they agitate in such a way that it sets off the electrons next to it, and those ones set off the electrons next to it, and so on. And they, by setting off in a cascade, they are all coherent. Last slide here. Last slide. Holograms. Just want to talk about holograms quickly. I'm not really going to go into a lot of detail. But a hologram, you've probably all seen one before. It's a 3D photograph. It's created through interference effects. So you can see, the star. It looks like it's three-dimensional even though it's not. It has a limited parallax. It's a weird word, but that means you can see around its sides to a limited extent. I mean, if you turn the hologram, you can sort of see the sides. You just can't see the back. So it's limited parallax. If you had a full parallax, you can see the back. This is how they're created, by the way.
Simple.
It's pretty complicated. You have to, and this is the film that you're putting it on. You have to send light through, you bounce it around, refract it, interfere it through lenses and slits and so on to get the exact right pattern to give you this effect.
Why does it look so simple up the top?
This is how it works.
Oh.
This is how they made that.
Oh, okay.
So, it's a very complicated process, but it has some interesting effects. One interesting effect of holograms is when you use visible light to see it, but small wavelength to create it, you get a magnification effect. So we haven't made them yet, but if you can create X-ray holograms, you would magnify the image thousands of times. If you use X-rays to make the hologram and then use visible light to look at it, that in itself would make the image much, much bigger. So an X-ray hologram could make perfect holograms of cells and the like because of this magnification effect. This happens because of longer wavelengths. I mean, holograms are getting huge these days. A few years back, Tupac, who's been dead for 12 years, more than that actually, 15 years. Tupac Shakur. He had a concert just about 3 years ago. They did a hologram of him on stage.
Oh my god.
There's pictures all on the internet of this hologram. But he's just an image. It's like a photograph, but he's three-dimensional. Of course, if you went to the round to the back, it'd stop working because it only has limited parallax. So it only works for the audience seats.
During it?
Yeah, he moved. Yeah. He didn't actually move. His image moved. He's dead. So,
Thanks for clearing that up.
but they did make a hologram of it. So this technology is getting really high. And anyways, it's created through interference effects. You use diffraction, refraction, reflection, all these effects combined in a specific way to create a hologram. Yeah.
That means soon we can have like the handheld hologram things from Star Wars.
Theoretically. One of the biggest problems is solving that parallax. Because the thing with the handheld ones from sci-fi is they have complete parallax where you can turn them all the way around.
Yeah, I don't think
Right
you can
now,
see-
we can't get that.
I don't think you can get see underneath it though.
It's the same thing, same concept, but beating that parallax is the trick that we're still working on. Okay, so that's it.
Cool.
What about the holograms and agents of S.H.I.E.L.D.?